When NASA's deep space sensors detected an unprecedented seismic pulse from the moon's core, renowned physicist Michio Kaku issued a stark warning that sent shockwaves through the scientific community. This mysterious signal, originating from deep within our celestial neighbor, challenges everything we thought we knew about the moon's geological state. Today on Sci and Why, we're unveiling the discovery that has top scientists on edge, and exploring why Kaku believes this could fundamentally change our understanding of the moon, and potentially impact Earth itself. The discovery that shook science. NASA's most sensitive instruments detected something impossible, a seismic pulse from the moon's core that shouldn't exist according to everything we know about lunar geology. The discovery began when NASA's Lunar Reconnaissance Orbiter and ground-based seismic monitoring stations detected an unusual signal emanating from deep within the moon's interior. Unlike the typical moonquakes recorded since the Apollo missions, this seismic activity originated from the lunar core itself, a region scientists believed had been geologically inactive for billions of years. The signal displayed characteristics that defied conventional understanding of how planetary cores behave in their final cooling stages. Dr. Renee Weber, from NASA's Marshall Space Flight Center, who leads lunar seismic research, described the readings as unprecedented in both their origin and intensity. The seismic pulse lasted several minutes and registered on multiple monitoring systems simultaneously, ruling out instrument error or external interference. What made this discovery particularly alarming was its timing, occurring just as NASA prepares to return humans to the moon through the Artemis program. The implications extend far beyond academic curiosity, potentially affecting the safety and feasibility of future lunar missions and permanent settlements. Michio Kaku's urgent warning. When one of the world's most respected physicists issues a public warning about lunar seismic activity, the scientific community takes notice. And Michio Kaku's message was unmistakable. Theoretical physicist Michio Kaku, known for his work on string theory and science communication, responded to NASA's findings with unprecedented urgency. During recent lectures and media appearances, Kaku emphasized that this seismic signal represents more than just scientific curiosity. It's a potential warning sign that humanity has overlooked for too long. We're witnessing the moon's core in what may be its final gasps of geological life, Kaku explained. But these death throes could have consequences we're only beginning to understand. His concern stems from the signal's implications for lunar stability, and its potential impact on Earth-Moon gravitational dynamics. Kaku pointed out that any changes in the moon's internal structure could affect its mass distribution, potentially altering its orbital characteristics over geological timescales. He stressed that while these changes wouldn't be catastrophic in human terms, they could accumulate over thousands of years to produce significant effects on Earth's climate and tidal systems. Kaku's warning has prompted increased funding for lunar seismic monitoring and accelerated timeline for deploying advanced instruments on the lunar surface. The moon's hidden internal structure. Beneath the moon's familiar face lies a complex internal structure that scientists are only now beginning to understand, and it's far more active than anyone expected. Modern research has revealed that the moon's internal structure resembles Earth's in miniature, featuring a solid inner core surrounded by a partially molten outer core. The inner core measures approximately 240 kilometers in radius and consists primarily of iron, while the outer core extends to about 350 to 360 kilometers from the moon's center. This structure was confirmed through analysis of Apollo seismic data and recent gravitational studies conducted by NASA's Grail mission. Billions of years ago, this core system generated a significant magnetic field, evidence of which exists in lunar rock samples brought back by Apollo astronauts. As the core cooled over geological time, this magnetic field weakened and eventually disappeared, leaving the moon without the protective magnetic shield that guards Earth from solar radiation. However, the core didn't simply shut down, it appears to be experiencing final phases of activity that modern instruments are now sensitive enough to detect. The recent seismic pulse suggests that the moon's interior is still undergoing significant changes, challenging the long-held assumption that our satellite is geologically dead. AI reveals hidden lunar secrets. Advanced artificial intelligence has uncovered hidden signals in 50-year-old Apollo data, revealing that the moon has been whispering secrets to us for decades. We just didn't know how to listen. Scientists at NASA's Jet Propulsion Laboratory have been feeding Apollo-era seismic data into modern machine learning algorithms, producing revolutionary discoveries about lunar internal activity. The original Apollo seismometers deployed between 1969 and 1972 recorded thousands of moonquakes, but analysis techniques from the 1970s could only scratch the surface of what the data contained. Today's AI systems can detect patterns and anomalies that were impossible to identify with vintage technology, distinguishing between genuine lunar activity and instrument artifacts with unprecedented precision. Dr. Sari Nunn, who leads the AI analysis project at JPL, describes the process as having a conversation with someone for 50 years, and suddenly realizing you've been missing half of what they've been saying. The AI has identified entire categories of seismic events that previous generations of researchers completely missed, including subtle signals that may have been precursors to the recent core activity. These discoveries suggest that the moon's interior has been more dynamic than previously thought, with ongoing processes that we're only now beginning to understand through advanced computational analysis. The shrinking moon phenomenon. The moon is actually shrinking before our eyes, and this contraction is creating dangerous fault lines that could threaten future lunar missions and settlements. As the moon's interior continues to cool, the entire satellite is contracting in volume, causing its brittle crust to wrinkle and form ridge-like features called lobate scarps. Some of these geological formations are remarkably young in astronomical terms, as recent as 200 million years old, indicating that this shrinkage process continues today. Dr. Thomas Waters from the Smithsonian's National Air and Space Museum has identified thousands of these thrust faults across the lunar surface, with many concentrated in the South Polar region where NASA plans to establish its Artemis base. The shrinking process creates internal stresses that can trigger moonquakes, some registering up to 5.5 on the Richter scale and lasting over 10 minutes. Unlike Earth's earthquakes, which typically fade quickly, moonquakes can continue reverberating for hours due to the moon's dry, fractured interior structure. This ongoing geological activity poses significant risks for future lunar infrastructure as the moon's surface consists of loosely consolidated regolith that becomes extremely unstable during seismic events. The recent core signal may indicate that this shrinkage process is accelerating or entering a new phase that could increase seismic hazards for lunar explorers. Implications for Artemis missions. NASA's plan to return humans to the moon faces an unexpected challenge. The lunar surface may be far more seismically active than mission planners anticipated. The timing of these seismic discoveries coincides with NASA's ambitious Artemis program, which aims to establish a permanent human presence near the moon's south pole by 2026. The same region targeted for lunar bases happens to be particularly vulnerable to moonquakes and landslides according to recent geological surveys. Dr. Nicholas Schmer from the University of Maryland warns that the moon's surface material, billions of years of pulverized rock from asteroid impacts, creates conditions where shaking and landslides can occur very easily. The planned Artemis base sites lie near several active fault systems that could pose serious risks to lunar infrastructure and crew safety. SpaceX's Starship human landing system, standing over 110 feet tall, with a relatively narrow landing footprint, could be particularly vulnerable to seismic activity. The recent core signal adds another layer of uncertainty to mission planning, as it suggests the moon's internal dynamics may be more unpredictable than previously thought. NASA has responded by accelerating development of the Lunar Environment Monitoring Station, or LEMS, a sophisticated seismometer suite designed to continuously monitor lunar seismic activity and provide early warning systems for future missions. The moon as Earth's cosmic stabilizer. You know, the moon doesn't just light up our night sky. It actually acts as Earth's gravitational anchor, preventing our planet from wobbling chaotically, and maintaining the stable climate that allowed life to flourish. The moon's gravitational influence goes way beyond just creating ocean tides. It fundamentally stabilizes Earth's axial tilt at about 23.5 degrees, and that's what gives us our predictable seasons. Without this lunar anchor, Earth would wobble chaotically like a spinning top, and that would lead to extreme climate swings, making complex life nearly impossible. Michio Kaku often points out that Earth is unusually stable for a planet its size, with the moon acting like, training wheels on a bicycle to prevent dangerous oscillations. This stability has remained constant for billions of years, which has allowed Earth's climate to stay suitable for the slow evolution of ecosystems, and eventually, human civilization itself. The moon's gravitational pull also creates these subtle bulges in Earth's crust, generating heat through tidal friction, and that actually contributes to our planet's internal geological activity. Any changes in the moon's internal structure could, potentially, affect this delicate gravitational relationship over geological timescales. And well, the recent seismic activity suggests that the moon's mass distribution may be shifting as its core undergoes final solidification phases, which could have subtle but cumulative effects on Earth's long-term climate stability, especially through alterations in Milankovitch cycles. Advanced seismic monitoring technology. NASA's next-generation lunar seismometers are about 30 times more sensitive than the instruments used during the Apollo era, and they're designed to detect even the faintest tremors coming from the moon's dying core. Two revolutionary seismic monitoring systems are actually preparing for lunar deployment as part of NASA's push to really deepen our understanding of what's happening inside the moon. Now, the Farside Seismic Suite, or FSS, is scheduled for deployment around 2026, and that'll be the first time humans have ever placed seismometers on the far side of the moon. This will let scientists triangulate seismic sources with a level of precision we've simply never had before. These instruments are honestly exponentially more sensitive than the Apollo devices, capable of picking up tremors that would have been totally invisible to 1970s technology. Meanwhile, the Lunar Environment Monitoring Station, or LEMS, is set to establish continuous seismic monitoring near the South Pole, running for months or even years to capture rare events and build up a long-term picture of lunar seismic behavior. Dr. Mark Panning from JPL says these instruments might finally confirm whether the moon experiences slow quakes like Earth's slow slip events, those gradual energy releases that take days to play out, and could explain that mysterious core signal. Extended observation periods will be absolutely crucial for figuring out whether this recent seismic activity is just a one-off or part of a much bigger pattern in the moon's geological evolution. The lunar core's final chapter. We're living in a rare cosmic moment, witnessing the final geological gasps of a world that's about to become truly dead for the first time in 4.5 billion years. Michio Kaku often points out how incredibly lucky humanity is to exist at just the right moment to observe the moon's internal dynamics before they disappear forever. In another billion years or so, the moon's core will probably freeze solid, ending the geological story that started way back when the solar system was formed. This recent seismic pulse could be one of the last chapters in this 4.5 billion year narrative, which makes our current observations scientifically priceless. Seeing things from this angle really transforms lunar exploration from just curiosity into a sort of urgent scientific priority. We're not just studying a neighboring world, but actually capturing data during a period that will never come again. The moon is giving us a live demonstration of how small planetary bodies evolve and eventually go geologically quiet. These observations are helping scientists understand similar processes on countless other worlds, from Mars to distant exoplanets. And the lessons we learn from the moon's core evolution could be crucial for figuring out which worlds might be habitable and how their geological activity impacts their ability to support life over cosmic timescales. Preparing for an uncertain lunar future. As humanity gets ready to return to the moon after a 50-year break, we're realizing that our closest celestial neighbor still hides some pretty dangerous secrets beneath its familiar surface. The combination of renewed lunar exploration and these surprising seismic discoveries is creating both new opportunities and new challenges for future missions. NASA's Artemis program now has to factor in seismic risks that just weren't fully understood back in the Apollo days, and that means we need thorough geological surveys before we can set up any permanent bases. The recent core signal really adds some urgency to getting those advanced monitoring systems up and running, so we can have early warnings for any dangerous seismic activity. Future lunar settlements are going to need some seriously robust engineering to withstand moonquakes that could last for hours, and even trigger devastating landslides in all that loose regolith. But, these challenges also open up a once-in-a-lifetime opportunity to study planetary evolution as it happens. Michio Kaku's warning is both a heads-up and a call to action. We've got to approach lunar exploration with a lot more respect for the moon's geological complexity. while also seizing this unique window to understand the fundamental processes that shape worlds across the universe. The moon's core might be dying, but its last signals could unlock secrets that totally change our understanding of planetary science and help guide humanity as we move out into the cosmos. Michio Kaku's warning about the moon's core activity really reminds us that even our most familiar celestial neighbor can still surprise us with hidden complexities. As we get ready to return to the lunar surface, these seismic discoveries are going to shape the way we build, explore, and survive on the moon. If you're fascinated by these cosmic mysteries and want to stay updated on the latest space discoveries, go ahead and hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more mind-bending explorations of our universe. Thanks for watching, keep looking up. When astronomers spotted a mysterious object racing through our solar system at 152,000 miles per hour, they knew they had discovered something extraordinary. Named 3I/Atlas, this colossal interstellar visitor is up to 10 times larger than the famous Oumuamua and represents only the third confirmed object from beyond our solar system. Today on Sci and Y, we're unveiling the incredible story of this massive cosmic wanderer that's rewriting our understanding of interstellar visitors and what lies between the stars. The discovery of a giant visitor. On July 1, 2025, astronomers using the Atlas telescope in Chile spotted something that would change our understanding of interstellar objects forever. The discovery began when the Atlas telescope in Rio Hurtado, Chile, detected a faint moving object against the backdrop of stars. Initially designated A11PL3Z, this mysterious visitor immediately caught attention due to its unusual trajectory and incredible speed of 152,000 miles per hour. Within hours, follow-up observations from telescopes worldwide confirmed what scientists had suspected. This was no ordinary comet or asteroid from our solar system. The object, now officially named 3I/Atlas, also designated C/2025N1, was traveling on a hyperbolic trajectory that could only mean one thing: it originated from interstellar space. Amateur astronomer Sam Dean played a crucial role by discovering pre-discovery images dating back to June 14th, allowing scientists to calculate its precise path. The Zwicky Transient Facility at Palomar Observatory and multiple Atlas telescopes provided additional confirmation data. Coming from the direction of Sagittarius near the galactic center, 3I/Atlas became the third confirmed interstellar visitor after 1I/Oumuamua in 2017 and 2I/Borisov in 2019, but this one was different. It was massive. A hyperbolic path through our solar system. 3I/Atlas follows the most extreme trajectory ever recorded for an interstellar object, with an orbital eccentricity of 6.15, far exceeding anything gravitationally bound to our sun. The comet's hyperbolic trajectory tells the story of an object that will visit our solar system only once before returning to the void between stars. With an eccentricity of 6.15, 3I/Atlas holds the record for the most extreme orbit among known interstellar objects, surpassing Oumuamua's 1.2 and Borisov's 3.4. Currently positioned about 670 million kilometers from the sun, the comet is racing inward at approximately 61 kilometers per second. Its path will take it dangerously close to Mars on October 2, 2025, passing within 29 million kilometers of the red planet. The comet reaches perihelion, its closest approach to the sun, on October 29, 2025, at a distance of 203 million kilometers, just inside Mars's orbit. Despite this close solar encounter, 3I/Atlas poses no threat to Earth, maintaining a safe distance of at least 269 million kilometers when it passes our planet on December 19, 2025. The comet's retrograde orbit, inclined 175 degrees to the ecliptic plane, confirms its extrasolar origin and suggests it has been traveling through interstellar space for millions of years. A colossal interstellar comet. Early estimates suggest 3I/Atlas could be between 6 and 20 kilometers in diameter, making it potentially the largest interstellar object ever discovered. The sheer size of 3I/Atlas sets it apart from previous interstellar visitors. While Oumuamua measured only about 100 to 1,000 meters in length, and Borisov was roughly 400 meters across, 3I/Atlas dwarfs, both with diameter estimates ranging from 6 to 20 kilometers. This massive scale makes it visible to ground-based telescopes despite being billions of kilometers away. The object displays clear cometary activity, developing a faint coma, a hazy envelope of gas and dust, as solar heating vaporizes ice on its surface. Observations by Gianluca Masi at the Virtual Telescope Project revealed the comet's magnitude at approximately 18.5, making it 2.5 million times fainter than Polaris, but still detectable with 150 to 200 millimeter telescopes equipped with CCD cameras. The reddish coloration observed on its surface suggests it contains primordial materials formed during the early development of its home star system. This ancient composition could provide unprecedented insights into planetary formation processes in other stellar systems. The combination of size, activity, and accessibility makes 3I/Atlas an extraordinary target for scientific study during its brief passage through our cosmic neighborhood. Global effort to study a cosmic visitor. Within hours of its discovery, 3I/Atlas became the focus of the most intensive international observational campaign ever mounted for an interstellar object. The astronomical community mobilized rapidly once 3I/Atlas was confirmed as interstellar. Dr. Karen Meach from the University of Hawaii led the coordination effort, stating, "Once 3I/Atlas was identified as likely interstellar, we mobilized rapidly. We activated observing time on major facilities." Ground-based observatories from Hawaii to Chile to South Africa began tracking the comet's movement, brightness, and spectral characteristics. The James Webb Space Telescope, with its unprecedented infrared sensitivity, provides crucial data about the comet's composition and thermal properties. Hubble Space Telescope contributes high-resolution imaging and ultraviolet observations that complement Webb's infrared capabilities. The European Space Agency's tracking stations monitor the comet's trajectory with extreme precision. Amateur astronomers worldwide have joined the effort, contributing valuable observations and helping extend the observational baseline. This collaborative approach ensures continuous monitoring as 3I/Atlas approaches the Sun and becomes increasingly active. The coordinated campaign represents the most comprehensive study of an interstellar visitor ever attempted, with data being shared in real time among research institutions globally. Scientists have only a limited window, from July through December 2025, to gather data before the comet fades beyond detection limits. Learning from past visitors, Oumuamua and Borisov. 3I/Atlas joins an exclusive club of interstellar visitors, but its characteristics challenge everything we learned from its predecessors. The discovery of 3I/Atlas provides crucial context for understanding interstellar objects by offering a third data point in this emerging field. Oumuamua, discovered in October 2017, puzzled scientists with its unusual elongated shape, mysterious acceleration, and lack of visible cometary activity. Its behavior sparked debates about whether it was a natural object or possibly artificial technology. Comet 2I/Borisov, found in August 2019 by amateur astronomer Gennady Borisov, appeared more familiar, a typical comet with a visible tail and predictable outgassing behavior. Now 3I/Atlas presents yet another variation, a massive, clearly active comet that behaves more like Borisov but on a much larger scale. Harvard astronomer Avi Loeb notes that 3I/Atlas's size and brightness make it an ideal target for detailed study, potentially resolving some mysteries left by Oumuamua. The three objects demonstrate the diversity of interstellar visitors, from mysterious cigar-shaped objects to familiar comets to massive primordial remnants. Each discovery refines our understanding of how planetary systems eject material and what types of objects travel between stars. The rapid succession of these discoveries suggests interstellar visitors may be far more common than previously thought. A window into the galactic past. Scientists believe 3I/Atlas originated from the thick disk of the Milky Way, making it potentially older than our entire solar system. Dynamical modeling by researchers at Oxford and Canterbury universities has traced 3I/Atlas's trajectory back through space and time, revealing its likely origin in the Milky Way's thick disk, a region containing some of the galaxy's oldest stars. This suggests the comet could be over 7 billion years old, predating our 4.6 billion-year-old solar system by billions of years. The object's reddish surface coloration supports this ancient origin, indicating it contains primordial materials that formed during the early epochs of galactic evolution. Dr. Mark Norris from the University of Central Lancashire explains that studying such ancient objects provides unprecedented insights into the conditions that existed when the galaxy was young. The comet's composition could reveal whether the chemical building blocks of life are common throughout the galaxy or unique to our local stellar neighborhood. Spectroscopic analysis of 3I/Atlas's coma and tail will help determine the ratios of water, carbon monoxide, methane, and other compounds, creating a chemical fingerprint of its distant birthplace. This data represents our first direct sample of material from the galaxy's ancient past, offering a unique opportunity to study stellar and planetary formation processes that occurred billions of years before Earth existed. Preparing for the next interstellar encounter. The discovery of 3I Atlas has accelerated plans for rapid response missions designed to intercept and study future interstellar visitors up close. While 3I Atlas was discovered too late for spacecraft interception, its arrival has galvanized the space community to prepare for future opportunities. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents the first spacecraft specifically designed to rendezvous with an interstellar object. The mission will remain in a parking orbit until a suitable target is identified, then rapidly deployed to intercept the visitor. NASA is developing similar rapid response capabilities, including concepts for small, fast spacecraft that could launch on short notice. The upcoming Vera Rubin Observatory will revolutionize interstellar object detection, photographing the entire visible sky every few nights and potentially discovering dozens of these visitors annually. Advanced artificial intelligence systems are being trained to automatically identify unusual trajectories that might indicate interstellar origin. Scientists estimate that with improved detection capabilities, we might discover several interstellar objects each year, rather than one every few years. The goal is to provide months or years of advance warning for future visitors, allowing time to plan and execute interception missions that could collect samples and perform detailed in-situ analysis of material from other star systems. A cosmic sensation captivates the world. The announcement of 3I Atlas has captured global attention, inspiring both scientific excitement and public fascination with our cosmic visitors. The discovery has generated honestly unprecedented media coverage and public interest in interstellar objects. Scientists like Avi Loeb and Mark Norris have become prominent voices explaining the significance of this cosmic visitor to audiences worldwide. Social media platforms are buzzing with images and updates from amateur astronomers who are contributing to the observational campaign. The comet's impressive size and clear cometary activity make it more accessible to public understanding than the mysterious Oumuamua ever was. Educational institutions are now incorporating 3I Atlas into curricula, using it to teach students about orbital mechanics, spectroscopy, and even the search for life beyond Earth. The discovery has also sparked renewed interest in SETI research and the possibility of detecting artificial objects among interstellar visitors. Science museums worldwide are creating special exhibits about interstellar objects, using 3I Atlas as a centerpiece to explore themes of cosmic evolution and humanity's place in the galaxy. The comet's journey through our solar system serves as a powerful reminder that we are part of a dynamic galactic ecosystem where material regularly travels between star systems. This cosmic perspective has really inspired philosophical discussions about the interconnectedness of stellar systems and the potential for life to spread throughout the galaxy. Unanswered questions and ongoing mysteries. Despite intensive study, 3I Atlas guards many secrets that continue to puzzle astronomers and challenge our understanding of interstellar objects. The comet's exact size remains uncertain due to its surrounding coma, which makes it tough to distinguish between the solid nucleus and the gas and dust envelope. Current estimates range from 6 to 20 kilometers, but the true size may not be known until the coma dissipates after perihelion. Scientists are also investigating the comet's rotation state, with some observations suggesting it may be tumbling chaotically rather than spinning smoothly, possibly indicating a violent collision or gravitational encounter in its past. The composition of 3I Atlas presents another puzzle. While it clearly contains water ice and other volatiles typical of comets, the exact ratios and presence of organic compounds still remain to be determined. Researchers are watching carefully for any signs of non-gravitational acceleration, similar to what was observed in Oumuamua, which could provide clues about the comet's internal structure and outgassing patterns. The object's brightness variations as it rotates may reveal information about its shape and surface features. Each new observation adds pieces to the puzzle, but many fundamental questions about 3I Atlas's origin, composition, and behavior remain unanswered, ensuring that this cosmic visitor will continue to challenge our understanding long after it leaves our solar system. A new chapter in cosmic exploration. The arrival of 3I Atlas marks the beginning of a new era in astronomy, where interstellar visitors become regular subjects of scientific study rather than just rare curiosities. The discovery confirms that interstellar objects are far more common than we previously thought, with estimates suggesting they may pass through our solar system multiple times per year. This realization is, honestly, transforming astronomy from a field focused primarily on our local cosmic neighborhood to one that regularly studies material from distant star systems. The data collected from 3I Atlas will inform the design of future space missions, ground-based observatories, and detection algorithms optimized for finding these cosmic messengers. As technology advances, humanity stands poised to learn about planetary formation, organic chemistry, and potentially even life itself through the study of interstellar visitors. The comet's passage through our solar system represents more than just a scientific opportunity. It's a reminder that the universe is far more dynamic and interconnected than we once believed. Each interstellar object carries with it the story of distant worlds, alien chemistry, and cosmic processes that shaped the galaxy long before Earth even existed. As we prepare for future visitors, 3I Atlas will be remembered as the massive cosmic wanderer that helped establish the study of interstellar objects as a fundamental branch of astronomy, opening new frontiers in our quest to understand the universe and our place within it. 3. I-Atlas has given us an unprecedented glimpse into the dynamic nature of our galaxy, where massive objects regularly travel between star systems carrying the secrets of distant worlds. As this colossal visitor continues its journey through our solar system, it reminds us that we are part of a vast cosmic community connected by these interstellar messengers. If you're fascinated by these cosmic discoveries, go ahead and hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more explorations of the universe's greatest mysteries. Thanks for watching. Keep looking up. When CERN's Large Hadron Collider smashed protons together at unprecedented energies, scientists weren't just hunting for new particles. They were searching for something far more extraordinary: microscopic black holes. These quantum-scale phenomena, predicted by cutting-edge theories involving extra dimensions, could revolutionize our understanding of gravity and space-time itself. Today on Sci and Y, we're unveiling what really happened when the world's most powerful particle accelerator went hunting for the universe's most mysterious objects. The quest for quantum black holes. CERN's scientists embarked on one of the most ambitious experiments in physics history, deliberately trying to create black holes in a laboratory setting. The search for microscopic black holes at CERN represents a fascinating intersection of theoretical physics and experimental reality. Unlike the massive black holes found in space, these quantum black holes would be incredibly tiny, existing at subatomic scales and lasting for mere fractions of a second. The CMS experiment at CERN's Large Hadron Collider has been actively searching for these phenomena since the facility's early operations. According to CERN's official documentation, some theoretical models suggest that microscopic black holes could form when particles collide with sufficient energy, particularly if our universe contains extra spatial dimensions beyond the familiar three. These theories, including the Arkani-Hamed-Dimopoulos-Dvali model and the Randall-Sundrum scenario, propose that gravity might be much stronger at quantum scales than previously thought. The LHC's proton-proton collisions at energies up to 13 TeV create conditions where, according to these models, space-time itself could briefly collapse into microscopic black holes. If formed, these quantum objects would immediately evaporate through Hawking radiation, producing distinctive particle signatures that CERN's sophisticated detectors could potentially observe. The theoretical foundation. The possibility of creating black holes in particle accelerators stems from revolutionary theories that suggest our universe has hidden dimensions we can't perceive. The theoretical framework for microscopic black hole production relies on models involving extra-spatial dimensions. In standard four-dimensional physics, creating a black hole would require concentrating energy equivalent to about 10 to the 19th GeV, far beyond any human-made technology. However, theories like the ADD model propose that gravity might propagate through additional dimensions, while other forces remain confined to our familiar three-dimensional space. This would effectively lower the energy threshold for black hole formation to potentially just a few TeV, precisely within the LHC's operational range. Dr. Lisa Randall and Raman Sundram developed influential models suggesting that if extra dimensions exist, the fundamental scale of gravity could be much lower than previously thought. These theories emerged to solve the hierarchy problem, explaining why gravity appears so much weaker than other fundamental forces. If correct, when protons collide at nearly light speed in the LHC, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. The mathematics behind these theories is elegant but complex, requiring sophisticated computational models to predict observable signatures. CERN's experimental search. Armed with the world's most sensitive particle detectors, CERN scientists began their systematic hunt for evidence of microscopic black hole creation. The CMS experiment at CERN has conducted extensive searches for microscopic black hole signatures in high-energy proton-proton collisions. Using data collected during the LHC's operations at 7 TeV center of mass energy, researchers analyzed collision events looking for the distinctive particle sprays that would result from black hole evaporation. According to CERN's published results, if microscopic black holes were produced, they would evaporate almost instantaneously through Hawking radiation, creating characteristic patterns of subatomic particles detectable by the CMS detector surrounding the collision point. The search methodology involved examining invariant mass spectra of particle jets, looking for anomalies that couldn't be explained by standard particle physics. Scientists used sophisticated Monte Carlo simulations to model expected black hole signatures, comparing these predictions against actual collision data. The ATLAS experiment has also conducted similar searches, analyzing electron plus jet and muon plus jet invariant mass spectra with 140 inverse femtobarns of collected data. These experiments represent some of the most sensitive searches ever conducted for quantum gravitational effects, pushing the boundaries of what's experimentally accessible in fundamental physics. The surprising results. After analyzing millions of particle collisions, CERN's results challenged expectations and honestly, revealed something unexpected about the nature of reality. The experimental searches conducted by both the CMS and ATLAS experiments have yielded some pretty fascinating results. No direct evidence for microscopic black hole production has been found in the energy ranges examined so far. The CMS experiment's analysis of 7 tera-electron-volt collisions ruled out the existence of microscopic black holes, up to masses of 3.5 to 4.5 tera-electron volts, for various theoretical models. More recently, the ATLAS experiment search using 13 tera-electron-volt collision data set even more stringent limits, excluding quantum black hole production up to 9.2 tera-electron volts in the Arkani-Hamed-Dimopoulos-Dvali model and 6.8 tera-electron volts in the Randall-Sundram model. These non-observations are actually scientifically significant because they constrain the parameters of extra-dimensional theories. The absence of black hole signatures at these energy scales suggests that either extra dimensions don't exist as these models predict, or the fundamental scale of gravity is higher than theorized. However, these results don't definitively rule out microscopic black holes. They simply push the energy threshold higher, potentially requiring future collider experiments with even greater energies to test these theories conclusively. Safety considerations and public concerns. The prospect of creating black holes on Earth sparked widespread public concern, forcing scientists to address some pretty fundamental questions about experimental safety. Public fears about CERN creating dangerous black holes have persisted since the LHC's inception, and honestly, they've been amplified by popular culture and social media speculation. CERN has consistently addressed these concerns through comprehensive safety assessments and public education. According to CERN's official safety documentation, any microscopic black holes produced would be perfectly safe because they would evaporate almost instantaneously through Hawking radiation. The fundamental safety argument relies on cosmic ray interactions. High-energy particles from space constantly bombard Earth's atmosphere with energies far exceeding the LHC's capabilities, up to 10 to the 20th electron volts. If dangerous black holes could be produced at LHC energies, cosmic rays would have already created them throughout Earth's 4.5 billion-year history. Dr. John Ellis and other CERN physicists have emphasized that even hypothetically stable microscopic black holes would be harmless because they would interact so weakly with ordinary matter that they would pass through Earth without effect. The LHC Safety Assessment Group concluded that the experiments pose no conceivable danger, with multiple independent reviews confirming these findings. Hawking radiation and quantum effects. Stephen Hawking's groundbreaking theory predicts that microscopic black holes wouldn't grow and consume matter. Instead, they would explode in bursts of quantum radiation. Hawking radiation theory, developed by Stephen Hawking in the 1970s, fundamentally changed our understanding of black hole behavior. According to this theory, black holes aren't completely black but emit radiation through quantum effects at their event horizons. For microscopic black holes, this process would be extraordinarily rapid. Objects with masses comparable to elementary particles would evaporate in approximately 10 to the minus 27 seconds. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. This creates a natural safety mechanism. Any microscopic black holes produced at CERN would immediately decay into standard model particles before they could interact with surrounding matter. The evaporation process would produce a distinctive spray of particles including photons, electrons, muons and quarks, creating detectable signatures in CERN's instruments. Theoretical calculations suggest that the temperature of Hawking radiation from a microscopic black hole would be incredibly high, potentially reaching 10 to the 17th Kelvin. This extreme temperature would cause the black hole to radiate away its entire mass almost instantaneously, making it impossible for such objects to grow or pose any danger to their surroundings. Implications for extra dimensions. The search for microscopic black holes at CERN represents honestly humanity's first experimental probe into the possibility that our universe contains hidden spatial dimensions. The theoretical models predicting microscopic black hole production are, intimately connected to theories of extra dimensions. These models suggest that our familiar three-dimensional space might actually be embedded in a higher dimensional reality, with gravity able to propagate through these additional dimensions, while other forces remain confined to our observable space. The ADD model, which was developed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, proposes that gravity appears weak because it spreads out through large extra dimensions. Meanwhile, the Randall-Sundrum model suggests that we live on a three-dimensional brain within a five-dimensional space, with gravity concentrated near our brain by the geometry of space-time itself. CERN's experimental limits on black hole production provide, crucial constraints on these theories. The absence of black hole signatures at current energy scales suggests that if extra dimensions exist, they must be smaller or configured differently than some models predict. These results represent the first experimental tests of quantum gravity theories, providing invaluable data for theoretical physicists working to understand the fundamental structure of spacetime and the unification of quantum mechanics with general relativity. Advanced detection methods. CERN's scientists, have developed some truly revolutionary detection techniques to identify the fleeting signatures of microscopic black holes among millions of particle collisions. The search for these tiny black holes required developing really sophisticated analysis techniques to distinguish potential black hole signatures from ordinary particle physics processes. The CMS and ATLAS detectors use these multi-layered systems, silicon trackers, electromagnetic calorimeters, and muon chambers, to reconstruct particle trajectories and energies with, honestly, extraordinary precision. Scientists have also developed specialized algorithms to identify the high multiplicity particle jets that would result from black hole evaporation, looking for events with unusually large numbers of particles produced in spherically symmetric patterns. On top of that, machine learning techniques have been employed to analyze vast data sets, training neural networks to recognize potential black hole signatures among the billions of collision events recorded. The analysis focuses on invariant mass distributions, searching for resonances or anomalies that just can't be explained by standard model processes. Researchers use Monte Carlo simulations, which incorporate various black hole models, to predict expected signatures, then compare these predictions against real data using statistical methods. The detection challenge is immense. Potential black hole events would be extremely rare, requiring analysis of petabytes of collision data to identify possible candidates among overwhelming backgrounds of ordinary particle interactions. future prospects, and higher energies. As CERN prepares for even more powerful experiments, the search for microscopic black holes is, well, entering a new phase with unprecedented energy scales. The high-luminosity LHC upgrade, which is scheduled for completion in the late 2020s, will actually increase collision rates by a factor of 10, providing vastly more data for rare event searches. This enhanced capability could push the search for microscopic black holes to higher mass scales, potentially reaching the thresholds predicted by some extra-dimensional models. Looking ahead, future collider projects, including the proposed future circular collider, with energies up to 100 TeV, would provide even more sensitive probes of quantum gravity effects. The increased energy and luminosity would allow scientists to explore black hole production at mass scales up to 50 TeV or higher, definitively testing many theoretical predictions. Advanced detector technologies under development like improved calorimetry and faster data acquisition systems will enhance the sensitivity to black hole signatures. Theoretical work is also continuing to refine predictions, with new models suggesting alternative signatures that might be more easily detectable. Really, the combination of higher energies, improved detectors, and more sophisticated analysis techniques may finally provide the experimental breakthrough needed to either discover microscopic black holes or definitively rule out their production at collider energies. The broader impact on physics. Whether CERN finds microscopic black holes or not, the search itself is, honestly, revolutionizing our understanding of fundamental physics and the nature of reality. The quest for microscopic black holes at CERN represents more than just hunting for exotic objects. It's really testing the very foundations of our understanding of space-time, gravity, and quantum mechanics. The experimental limits already established have constrained theories of extra dimensions and quantum gravity, forcing theorists to refine their models and develop new approaches to unifying fundamental forces. The sophisticated detection methods developed for black hole searches have advanced experimental techniques across particle physics, improving our ability to discover other new phenomena. The safety analyses conducted for these experiments have also deepened our understanding of cosmic ray interactions and astrophysical processes. Even negative results provide valuable scientific information, ruling out certain theoretical possibilities and guiding future research directions. The interdisciplinary nature of this research has fostered collaboration between particle physicists, cosmologists, and theoretical physicists, leading to new insights about the universe's structure. As CERN continues pushing the boundaries of experimental physics, the search for microscopic black holes remains a powerful probe of reality's deepest mysteries, potentially revealing whether our universe truly contains hidden dimensions and whether quantum mechanics and gravity can be unified into a single theoretical framework. CERN's search for microscopic black holes represents humanity's boldest attempt to probe the fundamental nature of reality itself. While no black holes have been detected yet, the journey has revolutionized our understanding of physics and pushed the boundaries of what's experimentally possible. If you're fascinated by these cutting-edge discoveries and want to explore more mind-bending physics mysteries, hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more journeys into the universe's deepest secrets. Thanks for watching. Keep questioning reality.